going to do permutation on a circle. The formula is given as such. However, we want to try to understand this. So I will give you one short example on a set of just 3 objects. We try to compare the difference when I arrange 3 objects in a row versus I want to put these 3 objects into a circle. What's the difference? So we know that if you're going to permute onto a row, 3 objects will be 3 factorial, and this number is 6. So there are 6 ways to place ABC onto a row, and I have actually listed those 6 cases down below here. These are all the 6 different arrangements of your ABC. So to visualize what a circle looks like, we're going to do this connection. Think of it as we connect the front to the back on a row, so that this now becomes a circle, just like the diagram on the right side. So we are converting from a row into a circle. You're going to see this ABC appearing from left to right, ABC. So let's do it for the first 3, and we further explain from here. When I connect the first to the last object, we form up a circle. If I were to read off from a circle, the problem with a circle is, how do you know where is the starting point? Because when we have got a row, this extreme left position is like the start point. This is like position 1. This end point at the right side is the last position, which is position 3. On a row, you have got a clear positioning, 1, 2, 3, and so on. However, when we go to a circle, there is no such position. I don't know where to start. Therefore, the concept for a circle is you can start from any position, but you just go clock or anti-clockwise, go in a fixed direction to read off the values. So this reads as the permutation for ABC. When I go clockwise starting from A, it reads as ABC. However, when I go to the second one, again, because there's no fixed starting, I may want to start from A again. We go clockwise once more. It still reads as ABC for the second diagram. Third diagram, similar, still ABC. So what I would like to point out here is, therefore, when we do that connection to a circle, these 3 cases are considered the same case on a circle. As long as when you read off in a certain direction, clockwise for example, and they all read the same, they will be the same case on a circle. So when I move on to the next 3 of them, let's connect up the first and the last. And all this gave me the diagram on the right side. What happens now if I start reading off from A and we go clockwise? They are no longer ABC. This reads as ACB. This is also ACB. This is also ACB. Which also implies the same concept from above. These 3 cases are the same case on a circle. Therefore, how many ways are there that we can arrange your 3 objects onto a circle? The number of ways will be, you take that 3 factorial you initially have and you do a division by 3. Because every 3 cases from a row becomes the same case on a circle on the right hand side. And hence this answer will be 2. So this is what you need to know generally. When you arrange for n objects onto a circle, or sometimes they say a round table, we take n factorial for the n objects, but we must divide by n. This formula is the same as n minus 1 factorial. Okay, why is that so? N factorial can be broken up into n times n minus 1 factorial. So if I further divide by n, then this n will cancel out. It will give me the n minus 1 factorial. When we solve for the problems later on, we should present with the minus 1. To indicate that you have taken care of arrangements onto a circle, that's why we do a subtraction by 1. Okay, so I will show you a series of questions where we apply this together with concepts that we have done before, such as separation, together, and so on. But we do it onto a circle. Let's go on to the next page. I'm going to show you immediately the differences for a row versus a circle. So there are 3 portions here. Could you just help me break it up maybe into 3 equal segments? We're going to solve side by side to compare the differences. And let me start with part A. I have got these 3 people called John, Paul, and Mary. How many ways can we arrange the 10 people such that they will be in a row? But those 3 people need to be seated separately. So this is a row question, nothing new, but we go through the concept so that we compare for circle. When you want to separate people, first step is not to permute them, but is to permute the other set. So permute the rest of the people first. You want to exclude John, Paul, and Mary. I put them onto a row, so that gives me 7 factorial. We slot in John, Paul, and Mary. Whenever you have a row, the slotting in will always be 1 more than the current set. If you have 7 here, there should be 8 slots because we can include the front and back. Okay, include the front and back. So in a row, always 1 extra slot. And eventually we will permute these 3 objects that we have placed in, which we go for another 3 factorial. So your number of ways will be 7 factorial, 8 choose 3, 3 factorial. Okay, then let me go on to B. I've changed the problem such that it is a round table. That is the only difference. I will still need John, Paul, and Mary to be separated. We are going to think through the same concepts, just that the values will be different in the calculation. We still do permuting the rest first, which means you want to exclude your John, Paul, Mary. If I exclude those 3 of them, it will be a 7 minus 1 factorial. Minus 1 because it's now a circle, a round table, you must minus 1. We then slot in your John, Paul, and Mary. But how many slots should we have on a circle? Okay, so let's say I draw in a circle. I just visualize for a small example of 3 people. If you only have 3 people, how many ways to slot people in between? These are the possible slots for the red color arrows. 3 people will only have 3 slots. It's not like a row where there's going to be extra. Okay, so therefore, to slot in John, Paul, Mary now on a circle, it is a 7 choose 3. It's not the same as a row just now. And eventually, we still need to permute this John, Paul, and Mary that we have placed in. To permute this 3 will be a 3 factorial. So one of the important things that I need you to know is, you will notice that on a circle, you subtract 1, but only at the first stage when you put them on a round table. Any subsequent ones do not minus 1. Okay, so I just put in a note here, only subtract 1 once per round table or a circle. And that subtraction of 1 should be at the first instance. When you try to put objects onto a circle, you minus 1 at the first step. Okay, any subsequent steps, do your usual permutation. And hence my final answer, we write it out, 7 minus 1 factorial, 7 choose 3, 3 factorial. Now last case, I'm going to illustrate what will happen to if you have a round table but your seats are numbered. So it's not the same chair in a way. You are numbering your chairs as 1, 2, 3, 4 all the way to 10. Now to understand this, okay, there's a big space below. Let me just draw out a small example. You can use the space below to draw there as well. Can we think about just a 3 chairs problem? on a round table, and I want my chairs to be numbered chairs. So can we have them to be numbered 1, 2, and 3? Okay, we understand for a small example, then you will know what to do when you have 10 chairs later on. So help me draw out 3 circles, where on my 3 circles, I already have the chairs placed in. The chairs are called 1, 2, and 3. And I would like to have my people being called persons A, B, and C. So chairs are 1, 2, 3. People are A, B, C. Can we try to arrange these 3 people A, B, C onto the round table? So it will look like person A went to seat 1. Person B went to seat 2. Person C went to seat 3. This is one possible way. But what if I rotate the people? We want to visualize as I will be rotating the people by 1 chair. So person A no longer sits at 1. Person A goes to 2. And so on. B, C. Is this considered a same or a different case? This is a different case, for example, because person A is not on the same chair anymore. If you're on a different number chair, it's a different case. So we just do one last rotation for you to see. I rotate one more time, A, B, C. All of them are different cases after that rotation of 1 chair. So what this means for us is, if I have 3 chairs on a round table, you are basically going to have 3 ways of rotating the people. Because every rotation that I have shown you here is going to be a new case. They are sitting on a different number. Okay, this will illustrate the reason why we have this box above. Whenever you have numbered seats, you are always going to multiply the arrangements by n. And that n is actually the number of seats available to you. Because of the rotation, as you rotate, you will get the people to a different number chair. Okay, but it's not just about numbering. The important thing is, this is about labeling. It's a labeled chair. So the chairs are non-identical. Every chair is different. That's why when you rotate the people, it is a different chair for each person. So let's finish up. How does that translate to a solution for the problem? Round table of 10 numbered seats. The same exact solution will carry on, except we take one extra step. So you have the same values. Okay, you don't think about the numbers at the start. The only difference is you multiply by 10. And that 10 is because there are 10 seats. Based on the number of seats available, number of seats.